All right. Morning, everyone. Just to let you know, the session is being recorded. If you remember, we started talking about nonlinear programming from the beginning. I told you that we're working on linear programming as LPs, and then we moved to integer linear programs, and then we moved to mixed integer linear programs. And I always told you that at some point, which is week 8 today, we'll move on nonlinear programming. We used to have a more intense and deep nonlinear programming content on this module, but then we decided to leave it for other modules. So I just give you sort of introduction on linear programming as I did for dynamic programming. And then as you have the introduction level information, in other modules, when you encounter with any nonlinear programming, you know how it works. At least what does it mean and how does it look like? And as a part of those modules, you will get a more intensive and more detailed sort of training on nonlinear optimization. So today what we will do is we will have sort of introduction that we will continue on next week as well. If I move to the next slide, this is the link to the Math Booster. So just removed it from the one that I shared with you because I thought that it might be expired. That's why I asked at the beginning before I started to record the lecture. Please, you have access to the Math Booster, so have a look at that one, because derivatives and those stuff are the things that we will use and we will talk about in the this week and next week. So and I will presume that you already know them, so I'm not going to teach you derivatives and those stuff. So please, if you haven't done that, please have a look at Math Booster and try to learn them. Let's start with a simple example to see how it works. Oops. With an example of how it works, nonlinear programming. The example that we have here is price optimization. So here you can see that in this figure, what we have is the price of a product. Obviously, there are different ways of like deciding on the price of the product. For instance, if you have a cost to produce the product, you may have a profit margin that you want to add to the price, and then you will sell them. For instance, if it costs you £10 to produce a product, and then your profit margin is like 20%. I mean, the cost, as I said, is not production cost, all the costs altogether. I mean, the holding cost, transportation cost, let's say, the store cost and those stuff, holding cost, everything is included, and it is still £10. And your profit margin is like 20%. You add this 20% to the price, which becomes like 12 as the price of the product, and you sell them. Obviously, it's not the only way that we decide, and it's not for all products. There are other products that you decide on the prices based on other criteria that you have. And this is what we have here. And when you decide on the price, essentially you want to maximize your profit or revenue or whatsoever that you have. This is price optimization, to decide on the price that will provide you with the maximum profit or revenue. Revenue, I mean, at the end of the day, it is profit for you. If you look at this simple statement that we have here, we want to decide on the price of a product. We know that the demand for the product is a function of the price. This is obvious, right? The more the price is, the less the demand is. The less the price is, the more the demand is. Touching something new. And it is obvious. I mean, you're talking about regular and normal products. There are some products always have this objection that there are some products that there are some people who are willing to pay more for them because they want to have sort of like unique product that not everyone has access to them. We're not talking about them. 99% of the products that we have, if you increase the price, the demand goes down, and if you reduce the price, the demand goes up. We're talking about those products. So obviously, we know that the demand is a function of the price, which means that the higher the price is, the lower the demand is. This is valid for a lower price that leads to a higher demand. The demand function is given, so this is what we have here as a part of this specific example that we have. So if we just have the pen and the color, this is our demand function. As you can see here, there is a negative coefficient for the price, which means that if you increase the price, the demand goes down because there is a negative coefficient here. And the other way around, if you reduce the price, the demand goes up. This is a very well-known and often used sort of demand function for regular products that we have. It's a linear function of the price with a negative coefficient for the price. Moreover, we cannot produce more than 200 products. That's also something that we have. So it's not like if you see here based on the product, based on the demand function, this is our demand. The demand is equal to 650 minus 12.5p, which is the price. So you can see here, if the price is equal to 0, then you can, based on the demand function that you have, the demand goes up to 650. But we have only capacity of producing or storage of 200 products. So you're not going to do that. And it's not sensible, right? You have a demand price is equal to 0. So it's not that much of profit that you can get. Do you want to formulate this problem as an optimization problem? Now, I want to ask you, what do you think? What is the decision variables? What are the decision variables in this problem? What do you think? What are we going to decide? What do we want to optimize? What do you think? Just write it in the chat box. What are price of the product? Fantastic. Price of the product is the thing that we want to decide, because this will optimize the revenue, which was said as the first comment in the chat box. So the decision variable here is the price of the product, because we want to maximize, we want to optimize the revenue of the company that we are considering here. Our pricing problem is to choose, our pricing problem is to choose the price P that maximizes the revenue considering the capacity limit. So the decision variable here here is the price of the product. So if we just formulate the objective function here, the objective function that we have is, what's the objective function? We said that's revenue, but in terms of verbally, can you write it? What should be multiplied by what to get the revenue here? Revenue is essentially price multiplied by demand as it is set. That is correct. This is what we have here. P is the price multiplied by the demand, which is a function of price itself. This is what we have. So is this something which is, but before that, just let me get rid of the inks. This is what we have, right? This is essentially our objective function, multiplication of the price with the demand, which is a function of price itself. And we have a capacity, right? We can't sell more than 200. This is something that we have. Now, if you write the open form of the objective function, I don't know why it goes to the next slide again and again. Just sorry for that. Let me just redo this and hopefully stop. So if you look at this one, what we have here is the multiplication of the price with the demand function. Demand function is a function of the price. So if you just open it up, 650p minus 12.5p squared. And essentially what we have here is the capacity constant. The capacity constant here says that whatever is demand should be less than or equal to 200, which is our capacity. Now, looking at this model, if I write it here, so this is max 650 minus 650p minus 12.5 p squared subject to 650 minus 12.5 p less than or equal to 200, and p is greater than or equal to 0. Is this like the ones that we already solved in the previous part of the module? It's not. You can see that the objective function here is not linear. The objective function that we have here is not linear because we have p squared. The unknown that we have is squared, so this is not non-linear. So this is non-linear. Remember that the linear function is ax plus by plus whatsoever that we have, a c. These are constants. X and y are our unknowns. Here you can see that the unknown that we have is multiplied by itself essentially, which makes the problem non-linear. I'm just trying to change the color of the pen. Okay, it is back. Sorry. This is non-linear because we know from linear programming that a linear function is a multiplication of unknowns and constants. But here we have p squared. Obviously, p squared looks like something like this, which is not linear. Now, if we formally write the non-linear programs that we have here, this is how it looks like. This is essentially the function that we have, which is a function of our unknowns. It doesn't need to be linear anymore. So you may have x1 squared plus x2 cubed plus 1 over x3 plus x1 multiplied by x3. So this doesn't need to be linear anymore, subject to some constraints. The constraints that we have, they are also a function of decision variables, and again, they don't need to be linear. They can be non-linear. For all of them, I just put them as a less than or equal to 0. This means that the right hand side is here, so it can be, for instance, x1 squared plus 2x1 x2 minus 3 is less than or equal to 0. The right hand side here is 3. Okay, so that's the way we wrote it here. If it is greater than or equal to, you know that you can multiply both sides by -1 and you get less than or equal to. So here what we have is minimization of the objective function, which might not be linear, subject to some constraints. Again, they may not be linear. So if even one of them, one of the objective function or one of the constraints is not linear, our problem becomes non-linear. Here what we have our decision variables and set of the constraints. We have m constraints here because we can see here that we have from f1 to fm as the number of the constraints, and we have n decision variables. If m is greater than 0, which means that we have at least one constraint, we call this non-linear optimization, which is constraint optimization. So non-linear constraint optimization, because we have at least one constraint here. If m is equal to 0, which means that we don't have any constraints, obviously it's called unconstrained optimization. So we have a set of decision variables here, as you can see, that we have from x1 to xn. It can be, again, the same sort of decision variables that we had in linear programming. It can be continuous, it can be binary, it can be integer. The constraints matters, and also the objective function, that they are non-linear. So if you have any constraint, we call them constraint optimization, and if there is no constraint that we have, it becomes unconstrained optimization. Now, unconstrained optimization, as you can see here, this is our objective function. There is no constraint that we have. So that's why you can see that we are on the left part of the Euclidean space, where the decision variables might be negative, because remember that non-negativity is also a constraint. And we don't have it here. Therefore, we just look for the optimal solution wherever it is. It can be a negative value as well. And obviously, as you can see here, this is our objective function and it's not linear. Remember that a linear function is like this. This is a linear function. This is a linear function. This is a linear function. This is not a linear function. And as I said, it is unconstrained, because as you can see here, we don't have any any sort of constraints which limits the values of our decision variables. Where is the minimum of this function? Can you tell me if you're minimizing this problem? Min f x1 to xn, whatever we have, is like two-dimensional, so it is n is equal to 2f fn, and that's all that we have. There is nothing else that we have subject to nothing. It is none. We don't have any non-negative constraints. We don't have any constraints or anything like that. So here what I'm asking is, where is the minimum of this function? Obviously you can see on the chat box you wrote the answer. Here is the minimum of this function, because this is the x-axis that we have and this is the y-axis. Obviously this is our where we are trying to optimize, or the horizontal and vertical axis that we have here. So here you can see what we have in the horizontal axis. It is -3, and then on the vertical axis we have -2. So essentially this is our optimal solution. This is the point that we have. The point of -3 and -2 is the minimum of this function. Okay, so obviously you can see this, and remember that if you remember from last week's workshop, the whole point of like linearity there was that we wanted the function to be differentiable. That's what we will see, what we was telling you, that the function should be differentiable. So here simply we can see this is our optimal solution. We have another function here. It is unconstant because there is nothing to limit the values of our decision variables. So the feasible region essentially is the Euclidean distance that we have, because it's two-dimensional here. Where is the minimum here? Here we have the minimum. It's not as straightforward as the previous. In the previous one, simply you could see that we have only one point that we focus on, which is our minimum. Obviously, all other points that you look in this Euclidean space have a better, I mean, a higher solution, not better, you're minimizing the problem, okay, have a higher value, therefore this is our minimum. But if you look at this one is obviously, from the figure that we have, is the minimum of the function that we have. However, there are other points. This is also, if you're careless and you don't look at this part of the figure, which is impossible for the figure visually, but in optimization, you may end up choosing this one as the minimum because it looks like a minimum one, but we call them differently. This one is a local minimum that we will discuss later, because locally this is minimum. Locally minimum mean that if you consider only this part of the function, which looks like small here, but it might be a massive space, this is minimum. But this one is minimum for the whole space that we have. This is globally. Global minimum. So this is local because locally, if you consider just space, limited space around the point, this is minimum. But this one, it is the global minimum because if you consider the whole space that you have, this is the minimum value that you can get. So both of them are essentially unconstrained optimization. We don't have any constraints. This one straightforward. You can find the optimal solution, the minimum point, which is this one. This one, you can see that there are like different points here. You may end up choosing them. Some of them might be local minimum, some of them are global minimum. Here, if you look at this one, do you see any local minimums? Do you see any local minimums here? What do you think? No? No? So is it the same as global? Okay, yes, local and global both will be the same. Yes, this is what I wanted to hear. So this is essentially, if you look at this point, for this space, this is minimum. So I can call this local minimum. This local minimum at the same time is the minimum of the whole space. So this is global minimum as well. Okay, so global minimum, global optimum is local optimum, but the other way around doesn't work because we have counterexample here. So you can see the global minimum here. Again, it is locally minimum for this one, but the local minimum is not global minimum. Okay, so every global optima is a local optima, but every local optima is not a global optima. Okay, that's very good. Now, if we move to constraint optimization, in both examples that I showed you here, you can see that we don't have any constraints, so that's why we call them unconstrained optimization. But we may have constraints, and it is very very likely to have constraints in our problems. And if you have constraints, and remember from linear programming and graphical solution method that I showed you, when you have the feasible region, what we do is we just have the isoline of the objective function, we move it toward the direction of improvement until the last point that we hit, and that becomes our optimal solution. And we do the same for here. The only thing is, if it was linear programming, in linear programming, we will have like a linear sort of like feasible region, which looks like this. But here you can see that because the constraints are not, the constraints might not be linear, then we may end up to have a feasible region which looks like this. This is still our objective function, which is linear, and we just move it toward this direction, which is the direction of improvement. Okay, and remember that for the case of linear programming, it is really obvious that which point is the last one of the corner points. That would become our optimal solution. But the case of non-linear programming, specifically if the feasible region, the constraints are non-linear, it is a different story. And remember that I was telling you last week that in linear programming, when you have the isoline, and when you move the isoline toward the direction of improvement, you always stay in the feasible region. This is unlike integer programming, where your feasible region is only integer points, and you may have when you're moving your ISO, just other points, when you move from one point to another one, essentially you're leaving the feasible region, because these parts that you're just passing, they are not integer. So, and I told you that this is something that we don't like it for linear programming. When it is the case, when you have a feasible region where you're, when you move from one point to another point, you never leave the feasible region. That's something that helps us to find the optimal solution faster. But here you can see, again, we have the same issue as we have for integer programming, that when you move the isoline of the objective function, which is this one, toward the direction of improvement, some parts remain inside of the feasible region, whereas other parts may not. So you're leaving the feasible region while, some part of your isoline. Because remember that the isoline that you have, every point on it can become the solution. So every part that it hits the point, it doesn't matter if it is essentially here, here, or here. Everything should be in the feasible region that you have, so any part can be. This is the issue that we have with the nonlinear programming. So in this example that I'm showing here on the slide, what we have is just erase it. When we are here, we think that this is the last point that we are hitting, but we can see that if we further continue toward this direction, there is another point that we can hit. So that becomes a challenge of nonlinear programming, that we have different points that we have. If you're not careful, you may end up to find this one, which might not be the global optima that we're looking for. Another example that we have here, that's the thing that we have. It is constraint optimization, but you can see that there are some constraints which are not linear, and also the objective function which is not linear. And this is the last point that we have, and this is our optimal solution. This brings us to the concept of convex functions. So convex functions are functions like this. It should look like a mug or a cup that you have. It's like this. This is a convex function, which is nice, because easily you can find the optimal solution, the global minima, which is the local minima at the same time. This is a convex function. As you can see, it is looking up, like a cup or like a mug that we have. And the thing here is that you can see essentially that it is like a cup. And also, if you choose any points on this 2 points, a pair of points, on this function and connect them to each other, you can see that the line is above the function. So what we have here, if you just, this is what we have for the function. This is the value that we get from the function, right? What we have here, the function, and if you just connect them this way, oh, really bad in the lines here. You can see the values of this function, the function and the line. You can see that if you connect them, the line that you have is always above the function that you have. So if you want to test, if you have a function which is drew, and then you want to, if you drew a function and then you want to see visually if the function is a convex function or not, what you do is you just choose 2 points on the function, connect them to each other, and see if the line is above the function itself. This is whereas this one. If you look at this one, unlike the previous one that we have, yes, you can find points and connect them. You can see that the function is below the line that you have, but there are points that you can this one. And if you connect them, you can see that this part is above the line. The line should be above the function to have a convex function, but this one, we can call it a convex function. So this was visually that you have, but most of the time you end up in the situation that you can draw the function. So you have to mathematically show that the function is a convex function. And mathematically, what we do is we write it formally like this. A function that we have, fx, is a convex function if all x1 and x2 points that we choose, and we introduce a lambda which is between 0 and 1, including 1 and 0 and 1, including 0 and 1, then this is the function should be less than or equal to the line that we have. So this is what we have. Let me just go back to this slide. I want to show you something. Just want to talk about linear combination. Okay. We have 2 points here. Let's say these are the points that we have, x1 and x2. Okay. We can find any points on this line by writing a linear combination of these 2 points. For example, if this is 2 and this is 12, okay, you can find different points and write them as a linear combination of x1 and x2. How we do that is it's ax1 plus bx2. x1, I know it is equal to 2, x2 is equal to 12. If I consider a as 0 and b as 1, I will get this equal to 12, which is this point itself. If you go the other way, if you consider this one as 1 and this one as 0, you will get this is 12 and this gives you 2. You may go as linear combination, as I said. You may change these coefficients, a and b. They can be other numbers as well. It's not linear combination. For it to become linear combination, the coefficients that we have, a and b, should be between 0 and 1. If it is like 1 and 1, for instance, what you get is 14. It's a point here, right? If you assume, as I said, if a and b, both of them are a and b are between 0 and 1, including 0 and 1, you will get numbers here. In case that a plus b is equal to 1, okay? Because if both of them are 0 and 1, you can see both of them are between 0 and 1, but you got 14, which is out of this part. Now, let me show you this. Let me erase these parts. Okay, oops. Oops, didn't want to erase that part. That's okay. Now, I just want to give you some examples. pen. Okay, here, for example, if a and b, the summation of a and b is equal to 1, a can be equal to 0.5, and b should be equal to 0 and 0.5, because I want the summation to become equal to 1. 0.5 multiplied by 2 plus 0.5 multiplied by 6 by 12, which gives us 6. This gives us 7, which is a point here, 7. 0. For instance, 2 and 0.8. This gives us another point, which is, if we multiply this one by 0.2, this gives us, it's not an integer value, but you can see still, this gives us a value between 2 and 12. It is simple, right? Mathematically, it is so simple to just see that it gives us a value between x1 and x2. So what we write here is, it is lambda x1 plus 1 minus lambda x2. I use a and b here, but this is lambda. So a and b, a plus b is equal to 1, which means that a is equal to 1 minus b, or b is equal to 1 minus a. This is exactly the same. So you can write this as ax1 plus 1 minus a x2. We just replace it by lambda. So this is the linear combination of the function that we have. This is what I wrote. This is what we have here. This is the linear combination of the points that we have. So you can see that what I have here, if you have 2 points, x1 and x2, then I can get with this function, lambda x1 plus 1 minus lambda x2. This gives me any point in between these 2 points, including themselves. This is what I can get. So this is essentially my x1 or y1 or whatsoever that you call it in the previous example that I showed you. But I want to get the functions value. It's not one-dimensional. The example that I showed you here, this is one-dimensional, 1D, and what I have here is x1 and x2. This is 2D. Okay, and in the example that we have here, you can see that we have x and y. So I have to change the things here. Essentially, what we have here, f of x gives us, we have this x here, f of x gives us a value which is here. Essentially, this is the y that we have. So what we have here, this gives us any value that we can get here. Because f of x1, this is, where is x1? This is f of x1. Because this is x1 and this is f of x2. This is what we try to do here. So essentially, any point that you just choose here, so it becomes this one, for instance, here, the value that you get is this one. And the associated value on the function is here. Okay? Another point that we have, just let me erase this to, this is what I'm trying to show. I'm trying to say, as I said, this line is above the function. If you choose a point here, the associated value is here. Okay? And then the same, this is an x here. The same value that you get from the function is here. And you can see that simply this value is less than this value. This is what we have here. So what I wrote here, these are all points that you can get here. And this is the value of this specific, the value of the function value of this specific point that we have. Okay, is it clear? I'm pretty sure it's not for 90% of you. That's totally fine. It's a bit complex, but it takes time to just digest it. We'll solve a few problems in the workshop this week, and then it becomes maybe easier for you to understand. But at this point, do you have any questions? So what we have here on the right-hand side, which is the greater part, this gives us the value that you get from here, which is the value of the linear combination of these two values that we have. Let me just erase them. So let me just show this. So f of x1 is this one. and then f of x2 is this one. Okay, we wrote a linear combination of this, any point here, and then this part is the function value of the linear combination of these two. So what we say here is that any points on this line gives us a value which is greater than or equal to the value that we get from the same point if we just plug it into the function itself, and this becomes a convex function. But why I'm showing you this, because in reality, if I go back to this slide, we won't get lucky all the time to be able to draw a function like this. This is something like x squared minus a, for instance. This is our f of x. This is so simple to draw it. If you draw it, and you can see visually that this is a convex function. This one is a bit like this one is a bit more complicated, but still you can draw this one and you can see if it is convex or not. But there are functions that you're not that lucky and you cannot get simply a drawing of the function to see if it is convex or not. So what you do is you have to mathematically show that this function is convex. And remember that from the example that I showed you, this is a and this is b, and a plus b is equal to 1. This is exactly the same. So rather than introducing two constants, we have one which is lambda, and we just replace the second one with 1 minus lambda. Is this a convex function now? Yes, you can see it obviously from the visualization that if you draw any line here, this line is always above the function itself. We only consider until here because this is x1 and this is x2. And for this range, we want to make sure that the line is above the function itself. The line is lambda f x1 plus 1 minus lambda f x2. This part, this function, is f of lambda x1 plus 1 minus x2. And we can show this, that this is always greater than or equal to this one if you just plug x squared here. We will do it in the workshop so that you will see mathematically how does it look. If you plug x squared to this one, so this becomes x1 squared, and this one becomes x2 squared. And if you just plug these ones as this is f of this one becomes lambda x1 plus 1 minus lambda x2 to the power 2. If you just open it up, at the end of the day, you will have something which is an obvious sort of mathematically obvious, which is something that we can accept. If you want, just try this at home if you have time, and then. But on Wednesday, as I said, we will work on this one. This is another function that we have, e to the power x. You can see that it goes until infinity, but still it is a convex function because if you choose any 2 points, still the line is above the function. Now, that's something that, as I said, visually you can just see if a function is convex by looking at its shape, and if it is like a cup, if you just choose 2 points and you just draw a line in between them, if the line is above the function, it becomes a convex function. And also mathematically, if you have the inequality, if you can show that this inequality is valid for this specific function, then it becomes convex function. There is another definition of the function, convex function. But before that, we have a question in the chat box. Lambda f of lambda x1 plus, is this our optimum function we're trying to solve for? Is it the global minimum point? Okay. The short answer is no. We are not trying to solve anything. So we're just talking about the property of a function. Okay, this is independent from optimization. Now I'm talking about function to see if this function is convex or not. That's all that we're trying to do. If it is function, it's a nice thing. It helps us with optimization. Okay, if a function is convex, that you can see simply that we have a global optima here. But if a function is not convex like this one, you may have local optima as well. So um, convex function, a function being convex, this is a property of the function. It's always valid. A function is always convex or not. Okay, so it's not something that we're doing with optimization at this point. We'll use this property in optimization. Now, a third definition of convex function, a twice differentiable function f is convex if and only if the second derivative is non-negative. Derivative, as we said, I expect you all to know derivative of certain simple and some functions, not all of them, but when you know derivative, it's simple to just take the derivative for different forms. Um, um, we will, I will refresh your mind on in the workshop, but still, I expect you to know. So if you take the derivative of a function twice, and if this the second derivative is non-negative, then the function is essentially a convex function. For instance, this one, if we take the first derivative, f of f prime x, we can write it this way, is 2x, and the second derivative is 2, and this is greater than or equal to 0. So we can say that this function is convex. This is the property of this function. So x squared every time, all the time, is a convex function. This is what we want to show. Okay, so we drew this one. We saw that this is the function that we have, and this is obviously visually we can see that this is convex. I'll show you in the workshop that we can use the definition to show that this function is convex, and also now we can see that the second derivative of this function is a non-negative value, therefore this is a convex function. Now we have concave functions as well. Convex versus concave. You can guess that. If a function is like this, which is a cup being upside down, this is a concave function. So if if a function f is concave if it's -1, if it is mirrored, then it is convex. So, and as I told you, just in this example, when we have just trying to okay, fantastic. As I just drew this one, this is x squared f x is equal to x squared, and this is gx, another function which is negative x squared. This is concave because the negative of this one, which is mirrored upside down, is convex. Okay, so an example, this is what we have here, the example that we have. So you can see that horizontally it is mirrored. If a convex function is horizontally mirrored, it becomes a concave function. Or alternatively, if you have a function and you want to see if it is concave, you can just mirror it, and you can see if the mirrored one is convex, the original one becomes a concave function. Now, this was function, right? So if you're talking about convex and concave function, if I go back, this one was convex, right? How about this one? Is it concave now? At this point, we didn't know that we didn't talk about concave functions. That's why I didn't ask, and I just called it non-convex. Is it a concave function? It's a concave function. It's not, because for the convex function, remember that we said that um, if you have any 2 points, the line should be above the function. You can guess if it is mirrored, like this one. If you choose any 2 points, you can see the function now is above the line. But here you can see some part of this function is convex, some other parts are concave, like this one. Therefore, this function is neither a convex or concave or convex function. So it is a non-convex function. Now, if we move on, just checking the time. Oops. Here we have a fine. There's some stuff that I want you to know for the workshop. Not that there are a few more slides that I have. The fine function is a linear function with a constant. So this was a linear function, if you remember, right? If you add a constant at the end, this becomes an affine function. This is called an affine function. This is just a name that we have. Linear function, we have an unknown multiplied by square, but constant, if you have a constant at the end, this becomes an affine function. An affine function is both convex and concave. This was a linear function, right? And if you choose 2 points, this is on the line. And remember, by the definition, we said that if the line is above the function, then it is convex. At the same time, above what we meant, by the way, is greater than or equality. That was the definition that we had, lambda fx1 plus 1 minus lambda fx2. For the definition of concave function, it is greater than or equality. So in both of them, you can see that we have equality. So we have to consider equality as well. As the line is on the function, this becomes both linear and it becomes both convex and concave function. So an example here that I'm showing in the slide is ax plus b. This one, for instance, if you choose any 2 points, you can see that the line is on the function, which is obvious. And because equality isn't considered for both convex and concave functions, this becomes both convex and concave function. There are functions that are not, they are neither convex and concave. I showed you that one. This is one of them. If you just draw it, you can use online tools to draw this one. And this is what you will get. This is very similar to the one just a few minutes ago I asked you. And you can see on some points it is below the function, and some points it is above the function. So this is neither convex or function, neither convex or concave. If you have n convex functions, f1 to fn, and n positive scalars, a1 to an, the combination of them becomes a convex function. We'll try to do this in the workshop. So x squared itself is a convex function. E to the power x is also a convex function. This combination, which we have two convex functions multiplied by only a constant, becomes a convex function as well. So we talked about convex functions. We also have convex sets. This is different. And we don't have concave sets. Essentially what we have here, if you have a set like this too, forget about the math. We'll discuss this in the workshop. If you could find 2 points, any 2 points that you have, and you just connect them to each other, if the whole line is inside of the set of points that you have, then this becomes a convex set. This is unlike this one, for instance. You have these 2 points, and if you connect them to each other, you can see that this part of the line is out of the set that you have, and this is not a convex set. So does it ring any bell? Is the feasible region of a linear programming a convex set? Because remember that I told you, when you move the isolandoses stuff, it's always inside of the feasible region. If you choose any points in the feasible region of an LP, the line always stays in the set. Given a function, convex function f, the set which is created by this convex function becomes a convex set. So this is our linear programming constraint that we have. We said that the constraint should be linear function less than or equal to the right hand side. This is a convex set. For instance, 3 3x1 plus 2x2 less than or equal to 12, it is a convex. It creates a convex set because this is like this, the half space that I showed you. And if you choose any 2 points here and you connect them, it is inside of the half space that we have. And finally, the intersection of n convex sets becomes a convex set. This is the feasible region. We'll discuss this in the workshop in more detail. So here we know that if you have several linear constraints, each of them, because they are linear, they become convex sets. An intersection of them, which forms the feasible region, it becomes also a convex set. Said that I'm slightly late. I'm going to stop here, and we will work on the last parts in more details in the workshop, because they need some examples for you. I'm pretty sure with the examples you will see better. We will solve some problems, and we will. I'm pretty sure that it becomes more clear to you. Great stuff. If you have any questions, you can stay and ask me. Otherwise, I will see some of you today and the rest of you tomorrow for AIP's workshop, and also Wednesday and Friday. I'm pretty sure that you will be full of me for these 2 weeks. See you later. If you want to leave, just feel free. Is price optimization similar to the pricing analytics course? I mean, we will discuss this in the, yes, we will discuss this in the pricing analytics. It's one of the examples that we have in pricing analytics. Can you explain that lambda slide? Lambda slide. Okay. So what I have here, so what I'm trying to do is, remember that this is the shape of the convex function, right? And I said that if the line is always above the function, line is above the function means that you have this point, and this point's function value is here. And then for the same x, the function value is here. So this value is always greater than this one, okay? I can't go and check them one by one, right? So what I do is I write this one. This is essentially, we have x1 here and we have x2 here, okay? This gives me all values here, because this lambda 1 minus lambda, this is the linear combination, as I told you. This always gives me a value between f of x1 and f of x2, which are here. And I want to show that any value that I get here is greater than the associated, for instance, this is the value which comes from here, right? And the same x gives the function value of here. The function value is this one, because this point here is the linear combination of these two. This point here is lambda x1 plus 1 minus lambda x2. Okay? And f of this gives me this one. This is what I'm trying to show. This one, f of this one, is always less than or equal to what I get from here, which is lambda of fx1 plus 1 minus lambda of fx2. Okay? If it's still a bit vague, we will go through this in the workshop. Can I please explain affine functions again? Affine function is essentially a linear function with a constant at the end. That's all. This is a linear function because we have unknowns multiplied by the constants. Another constant is added at the very end. 3x1 plus 2x2 plus 12. This is an affine function, while x1 plus 2x2 is a linear function. This is a linear function, and this is an affine function. But it is both convex and concave. So definition of convex function is this, okay? This is convex function, right? Definition of concave becomes greater than or equal to, because remember that we're going to, if you multiply this function fx with -1, this becomes concave. Okay? It's like this, almost. And you can see the line is always below the function. So if it is concave, it becomes greater than or equal to. So you can see here that we have equality as well. It doesn't need to be always above. It can be on it for the convex function, for the concave function. Therefore, when you have a linear function like this, any point on them, you can see that it is on the line. So it satisfies this one and also this one. So it becomes both convex and concave. Fantastic. Any other questions? If there are more than two variables, example, complex optimization problem, we need to use other methods to check convexity. Yes, of course. But if even two, are you able to draw this yourself? This one. Are you able to draw this or not? But I'm really, I know a few functions, the drawing, so it's not something that we can do. So for any complex function that you don't know the shape, then you have to use the definition or the second derivative to make sure that the function is convex, concave. The last two slides. This one and this one, Emil. So definition of convex set is that if you choose any 2 points in the set and you connect them, the line should be inside of the set. We have this one, if you remember from linear programming, this is the half space. Remember that we draw the line and then we know below or above it, and it just divides the space to two half spaces. Those are sort of explained. And this is a half space that we have, and this is the set that we have. Set of all points. There are different points here, right? One point is, for instance, 0.5 and 1, 0.5 and 2. Here is 0.8 and 10, for instance. There are all different points that we have. So any 2 points that you choose here and you connect them, the line is also in the whole space, half a space that you have. So this becomes a convex set. Here it says, if you have one half a space, which is this one, okay? This is the half a space that you have. And this is a convex set because it is something less than or equal to something. This is a convex set. And we have another one which shows this part. And this is the intersection of these two. Both of them are convex because both of them are half spaces. Intersection of them that you have is here. And this is also convex. So by definition, you know that. If you show that this is convex set, this is a convex set, then the intersection of these two becomes a convex set, which is the feasible region of linear programming. Fantastic. Any other questions?
Okay, if you don't have any other questions, I'm gonna stop here. Let me first stop recording.